Hello, I'm Richard Overdorf, and I'm an engineer at Agilent Santa Rosa, where we do research and development for signal analyzers. Today, we're going to compare the Agilent real-time PXA with the Tektronix RSA 6000 series and its 110 megahertz of bandwidth. This comparison will focus on key performance parameters typically influence the ability to identify and measure intermittent or transient signals. We're also going to look at interference or signals within signals. I'm going to highlight standard attributes that can be verified from each of the instrument specification guides. The PXA has exceptional dynamic range. The TOI performance is an indication of how well the PXA handles large signals. The sensitivity or DANL of the PXA is also industry leading. We're going to show a couple of examples of why this is important for real-time analysis. In our instrument setup, we have two PSG signal generators we are going to use to generate two pulses, one large pulse and one small pulse at X band. These signals will be very close in frequency and overlap one another. Finding a small intermittent pulse in the presence of a larger pulse is a common use case for radar and electronic warfare. I'm going to optimize each instrument to make this challenging dynamic range measurement. The PXA can measure the signal accurately with 16 dB of attenuation. Fortunately, the PXA has 2 dB step attenuation in RTSA mode to help find the dynamic range sweet spot. A preamp will not work well here because of the larger input signal. Next, we want to identify a hard-to-find intermittent signal. We're going to use a splitter and feed the same signal into each instrument. The signal has a period of 1 second and a duration of 4 microseconds. In addition, we're going to place the signal close to the noise floor at a power level of minus 63 dBm, not including the splitter's attenuation. The probability of detecting a signal is a function of multiple things. One factor is how much power the signal of interest has in relationship to a threshold, or in this case, the noise floor. This is why the instrument's raw noise performance becomes important for detecting intermittent signals. The PXA has approximately 5 dB better noise performance here. It also has the widest real-time bandwidth and a higher sample rate, which also improves its probability of intercept. The PXA is doing a much better job of catching the signal every second. The Tech RSA has the ability to go narrow in RBW, which improves noise performance. I'm going to lower the RBW to further lower the noise floor. As you can see, the RSA is still not catching the signal as consistently as the PXA. This is because the trade-off between lower RBW is degraded POI. I measured the noise level of the Tech RSA at 3 specific RBWs. At these same RBWs, I also recorded the POI spec from the RSA's datasheet. I did the same with the PXA. This graph shows the PXA and RSA's minimum signal duration POI spec at each noise level. You can see that at a given noise level, the PXA can detect shorter signals than the RSA, or in other words, has a much better POI at a specified noise level. Another way to look at this is that for a specific signal duration, the PXA is able to measure a lower level signal. Overall, the PXA does a better job at finding intermittent signals, primarily because it has a higher sample rate and better noise performance. Perhaps more important is the fact that the PXA is not only the highest performing real-time analyzer, but also has the ability to make many must-have measurements such as wide-range swept spurious or EMI measurements, as well as noise figure and phase noise. In addition, the PXA offers the performance needed by the more stringent requirements for both radar and communication systems. From fast sweep times for wider spurious scans, excellent amplitude accuracy for uncertainty and repeatability, to more than 20 dB better phase noise. The ability to make both standard-based measurements as well as the real-time measurements allow for the most cost-effective solution for even the highest performing requirements. In summary, we have seen how the PXA's superior dynamic range enables it to see small intermittent signals in the presence of larger ones. We showed the PXA finding low-level intermittent signals with the best probability of intercept available on the market today. Finally, we reviewed how the PXA can make other must-have measurements needed by most engineers. To learn more about Agilent's real-time signal analysis, please visit the site listed or view more real-time PXA videos. Thanks for watching.